This is a presentation of our paper, Continual 3D Convolutional Neural Networks for Real-Time Processing of Videos. 3D CNNs are great. They reuse principles from 2D CNNs for image recognition, but with 3D filters in place of 2D kernels. Given enough data, they are both effective, achieving high accuracy, and computationally efficient for spatio-temporal input data. We evaluated some state-of-the-art methods for human activity recognition from recent years thoroughly and found that while they are efficient for offline, batch-wise inference, they are less so for online stream processing, where we want an immediate prediction for each frame as it arrives in our stream. Let me illustrate. Here you see a spatio-temporal input with time instances denoted by Roman letters and a 3D convolutional kernel with Greek letters denoting temporal positions. A 3D convolution is usually applied on the whole spatio-temporal input to obtain our output. At time t, our most recent frame is d. What happens when we receive the next frame? We can use sliding window processing of the input by discarding the oldest frame a and appending a new frame e while caching the other frames. Then the 3D convolutional kernel can be applied as usual. But the only new information we have computed came from the frame e. The remaining outputs provided redundant information. Let's restructure the convolution to handle per frame spatio-temporal 3D convolutions efficiently. A good way, we found, is to handle all kernel interactions upfront immediately when a frame is received. In practice, this amounts to applying the convolution on a zero-padded frame input and then aggregating the partial results when relevant. We named this approach Continual Convolutions with reference to the continual, never-ending nature of the input stream it can handle. The continual convolution is easily implemented as seen in the Python-style pseudocode. We have also provided ready-to-use PyTorch modules in the continual inference library, which is readily downloadable via the Python package index. For those interested, we have a paper at the ECCV CATL workshop this year, which gives a comprehensive introduction to continual inference networks, as well as the details of the library design. Using continual convolutions, we can now reuse existing 3D CNNs for truly efficient online stream processing. Importantly, our continual 3D CNNs are weight compatible with regular 3D CNNs, so they don't require retraining. Moreover, they can reduce the peak memory consumption, all while retaining similar accuracy. Let's dive into how continual 3D CNNs can be constructed. First, you replace the regular convolutions with continual convolutions. Next, we need to delay residual connections. Why? Consider the operation of a residual module with equal padding during offline inference. This is how most 3D CNNs are designed. Here the computation of a single output step is actually acausal since it uses information from the next frame in the computation of the current output. Transforming it to perform continual online inference, which must be causal, the residual needs to be delayed in correspondence with the convolution to keep alignment. Seems like a hassle, right? The continual inference library provides components to handle this automatically. Then you remove temporal end padding with zeros. Why? If we don't have padded zeros, each input gives one output. Everything works out. But with zero padding, each zero amounts to an additional output. This even stacks throughout convolutional layers as illustrated with the red boxes on the right. Note, however, that the removal of temporal zero padding leads to a model shift compared to the source model, which reduces accuracy. But we can improve the performance by extending the network receptive field. Since per frame computational complexity is constant with respect to continual convolutions and normalization layers, we can use the trick of increasing the global average pooling size at the end of the network to regain predictive performance. The pooling size is denoted for each point on the graph on the right hand side. Now to our human activity recognition benchmarks and kinetics 400 and charades, where our approach is to reuse an existing 3D CNN and transfer its model weights to a corresponding continual 3D CNN to accelerate it, as well as extend its receptive field to increase accuracy. This resulted in state-of-the-art per-frame accuracy efficiency trade-offs as seen by the circled Pareto frontier, and very good computational and memory improvements compared to source models, as well as the ability to do real-time human activity recognition on a laptop. Thanks.